Hello and welcome to this explainer. Today we're exploring one of the most fascinating, mind-bending, and extreme environments in the entire universe. We are looking right into the absolute heart of matter itself, the atomic nucleus. If you've ever wondered what's actually holding the fundamental building blocks of our reality together, well, you're in the exact right place.
Okay, let's dive into this. Here is our roadmap. First, inside the atomic nucleus. Second, the nuclear stability puzzle. Third, mass defect and binding energy. And fourth, the laws of radioactive decay.
Section 1. Inside the atomic nucleus, a question of scale.
Before we get into the really crazy forces at play here, we have to understand the sheer, mind-blowing proportions of an atom. The radius of a typical atom is on the order of 10 to the negative 10 meters, but the nucleus, it's on the order of 10 to the negative 15 meters, which we call a Fermi. To really wrap your head around this massive scale difference, think about this analogy. If an entire atom were enlarged to the size of your classroom, the nucleus would be nothing more than a tiny pinhead sitting right in the center. And we've known this since Ernest Rutherford's famous alpha particle scattering experiments back in 1911. The Rutherford model proved that an atom isn't just some solid block. It's actually mostly vast, completely empty space. But more than 99.9% of its mass is concentrated in that tiny, dense, positively charged core. So what is actually sitting inside that tiny pinhead? Well, since James Chadwick's discovery in 1932, we've known the nucleus is made up of two fundamental particles, positively charged protons and neutral neutrons. Collectively, we just call these nucleons, and the total number of these nucleons gives us the atomic mass number, which we denote with a capital A. Now, because practically all of an atom's mass is packed into a space that is 10,000 times smaller than the atom itself, we get this insanely huge number for nuclear density, 2.3 times 10 to the 17 kilograms per cubic meter. To give you a sense of how extreme that is, the density of ordinary water is just 10 to the 3 kilograms per cubic meter. To put that into perspective for you, a piece of nuclear material the exact size of a sugar cube would weigh billions of tons, literally. But here's the really wild part. That staggering density, it's actually a constant. Experimental data shows us that the volume of a nucleus is directly proportional to its mass number. That basically means if you take a larger nucleus and pack in more protons and neutrons, it simply takes up more space, kind of like adding water to a liquid drop. The physical size of the nucleus increases, but that incredibly high density remains exactly the same across all nuclei.
Section 2. The nuclear stability puzzle. Battling forces.
All right, let's think about this logically. We've got a microscopic, incredibly dense ball packed completely full of positively charged protons. How on earth can a nucleus possibly hold itself together without just blowing apart? If you take two protons separated by a typical nuclear distance, like 2 femtometers, the electrostatic Coulomb force pushing them away from each other is an enormous 58 newtons. That is huge on a subatomic scale. You might think, oh, maybe gravity pulls them together, but calculating the gravitational force gives us a minuscule 4.6 times 10 to the negative 35 newtons. Gravity is utterly, completely crushed by the repulsive electrical force. And that glaring physical impossibility, the fact that nuclei exist at all, when the math literally says they should fly apart, leads us to a monumental conclusion. There must be a third, vastly more powerful force of nature at play here, the strong nuclear force. And this brilliantly illustrates that exact battle. The short-range, strong nuclear force swoops in to overpower the long-range Coulomb repulsion. The net effect of that, the nucleus manages to stay firmly bound. Now, this strong force has some incredibly unique traits. First up, it is the strongest fundamental force in nature. It's about 100 times stronger than the Coulomb force. Second, it's extremely short-range, operating only over a distance of 1 to 2 femtometers. Third, it is charge-independent, meaning it pulls a proton and a proton together with the exact same strength as a neutron and a neutron. And finally, it has a saturative nature. That means a nucleon only really interacts with its nearest immediate neighbors, not every single particle in the whole nucleus.
Section 3. Mass defect and binding energy. Missing mass?
Okay, so we know what force holds the nucleus together. But what happens to the actual physical mass of these nucleons when this incredibly strong force binds them? Well, we encounter this bizarre subatomic reality known as the mass defect.
If you take the individual masses of all the free protons and neutrons that make up a nucleus, and you add them together, they weigh more than the actual assembled nucleus. I know, right? It sounds crazy, but it's true. A whole nucleus actually weighs slightly less than the sum of its individual parts.
So where did that missing mass actually go? Well, for that, we turn to Albert Einstein's famous equivalence principle, E equals mc squared. That missing mass, or mass defect, was converted directly into energy during the formation of the nucleus. And this is what we call the binding energy. It's the exact amount of energy you would need to supply if you somehow wanted to break that nucleus back apart into free nucleons. And this isn't just some abstract textbook concept. This literally governs the universe. When we look at the binding energy curve across different mass numbers, we see that tapping into this energy is actually possible. Through nuclear fission, which is splitting heavy, less stable nuclei, or nuclear fusion, which is joining light nuclei together, we release this massive, massive binding energy. And that is exactly what powers our atomic reactors here on Earth and every single star in the night sky.
Section 4. The laws of radioactive decay when stability fails.
But what happens when that delicate balance of forces inside a nucleus isn't quite perfect? Well, when a nucleus is unstable, it has to shed energy or mass to reach a more stable state. And it primarily does this in 3 ways. Alpha decay, where it spits out a helium nucleus; beta decay, where it emits fast-moving electrons or positrons; and gamma decay, where it releases its excess energy as high-energy photons. But here's the catch. You absolutely cannot predict exactly when a single specific unstable nucleus is going to decay. Radioactive decay is fundamentally a game of probability. Each radioactive species is governed by a unique decay constant, which we represent with the Greek letter lambda. This is a fixed probability of decay per unit time. And amazingly, it is completely independent of external conditions. It doesn't care about temperature, it doesn't care about pressure, it just decays at its own probability rate. Now, what's really interesting is how we use that individual probability to predict the behavior of millions of atoms. Using a bit of calculus, we integrate the fact that the rate of decay is directly proportional to the number of undecayed atoms currently present. And that gives us the famous radioactive decay law. N of T equals N0 times e to the power of negative lambda T.
And when you plot that mathematical law out, you get this beautiful exponential decay curve. It perfectly shows the radioactive activity dropping off over time. We can map 2 vital concepts onto this curve. The half-life, which is simply the time it takes for exactly half of the radioactive sample to disintegrate, and the mean life, which is the average lifetime of all the nuclei in the sample. Both of these show us that, mathematically speaking, it technically takes an infinite amount of time for the entire material to completely disintegrate.
So we've journeyed from the incomprehensibly small radius of a pinhead nucleus to the massive binding energies that hold the universe together, all the way to the exponential laws that govern their decay. I want to leave you with this final thought. If the tiny mass defect hidden inside everyday atoms holds enough energy to power the stars, what other untapped forces are sitting quietly right in front of you? Thank you so much for joining me on this explainer. Keep questioning and keep exploring.